Hello children, good morning. We are going to study about atomic structure. So just let us just recap what you have studied in your ninth standard. You know that matter is composed of smallest particle. So what is the smallest particle called as atom? Uh, Atom was first with proofs. It was proved that matter is composed of smallest particle called as atom. The scientist who has said that matter is composed of smallest particle is Dalton. That's why we call it as the Dalton's theory. So according to him, atom is indivisible and matter is composed of smallest particles. Later, we got many scientists. So this theory was proposed in 1800s. Later, many scientists have given theories on the structure of the atom. So later it was found that atom consists of subatomic particles. Subatomic particles means particles which are present inside the atom. So what were the subatomic particles which were discovered later? They were electrons, protons, and neutrons. Electrons are negatively charged particles, protons are positively charged particles, and neutrons are neutral particles. So later, the discussion was there on how are these particles arranged inside the atom. So how do you think these atoms were arranged, these subatomic particles were arranged inside an atom? All of us, we know that atom is neutral. Electrically, it is neutral. So if we say positive particles are there, negative particles are there, neutral particles are there, it should have some charge. But overall, we see that atom is highly stable and it is electrically neutral. So we got about many theories. So let's just see what are the theories which you have studied in your ninth standard. A quick recap of what you have learned. Let us have the theories. The first theory which you have studied was Thomson's atomic model. It was Thomson's atomic model. And what was the other theory you have come across? It was Rutherford's model of an atom. Rutherford's model of an atom. Then you have come across Bohr's model of an atom. Bohr's model of an atom. So let's have a quick recap of what Thomson has told. So what did Thomson tell? So let us first just recollect what Thomson has taught. So we are just discussing about the Thomson's model. So what did Thomson tell us about the atomic model? So he said that if we assume this is an atom, he said that positive charge is dispersed inside the atom. Just like in watermelon, let me put this positive charge in the form of red, because this model is also called as watermelon model. He compared the positive charge to the pulp inside a watermelon. So he said that the positive charge is spread out inside the atom, just like the pulp, the pink color pulp inside the watermelon. Just visualize, imagine that this is a watermelon and how the pulp is there. In that way, this positive charge is spread out inside the atom. Then what did he say? Where are these electrons present? He said that inside this pulp, just how the seeds of watermelon are embedded inside the pulp, the same way the negative charge of an atom is also embedded inside the atom. So you have the pulp inside, that is the positive charge, and inside that you have the electrons which are spread out just like the seeds in watermelon. So we call this model as watermelon, sorry, it is also called as the watermelon model of an atom. So according to this Thomson's model, if we imagine that positive charges spread out and electrons are also there, what will happen is positive and negative charge get cancelled. So what happens is atom should become atom should collapse. So if they cancel each other, so what will happen? It becomes the atom should collapse. The atom should collapse. So is it happening there? Atom should collapse. So are we able to see the atom collapse here? No, atom is not collapsing. So the later model, as Thomson could not explain the stability of the atom, the later model was proposed by Rutherford. So how did Rutherford explain? He explained it through a model, through his experiment that is called as alpha ray scattering experiment. And he gave the model of Rutherford, what model he has given, we call the model as, what is the model of Rutherford given by us? It's also called as planetary model. Planetary model. So what does this planetary model explain? Planetary model explains that just like how, if we imagine this is a nucleus which is present at the center, he said that the electrons revolve around the nucleus in circular orbits. So he gave the concept that just how the electrons, just how the planets revolve around the nucleus, sorry, how the planets revolve around the sun, the same way he said that if we imagine we have an electron here at this particular place, so he said that just like how the planets revolve around the sun, same way electrons also revolve around the center of the atom, that's called as the nucleus. So according to this theory, if we imagine, 1 minute, let me draw the electron here. Let me show an electron, small electron on this particular place. It's in red color. So as the electron is revolving around this in the circular orbit, what will happen is electron should lose energy. So once the electron loses energy, what will happen to the electron? Once it loses its energy, it should fall into the nucleus. So once the electron falls into the nucleus, what will happen to the atom? It will collapse. The atom has to collapse. So, but we see that atom is stable. So Rutherford's model could not account for the stability of an atom. So the next model which was given by Bose model. Bose model was successful as he has given the concept of stationary orbits. So the Bose model was successful because he has given the concept of stationary orbits. So what was the concept he has given? Stationary orbits concept he has given. So what does a stationary orbit mean? As long as the electron revolves around the nucleus in particular orbit, it will neither gain energy nor it will lose energy. So according to this, if it is in a second orbit, if the electron is in second orbit, if it jumps to the first orbit, it will emit energy. If it is in the lower level, that is if it is in first orbit, and if it's jumping into second orbit or third orbit, it will absorb energy which is equal to the difference in energy levels of the two orbits. So how is this energy going to be emitted? This energy is always emitted in the form of light. So this energy is emitted in the form of a radiation. We call it as radiation. So how do you see this radiation? It is seen either in the form of the radiation which is emitted, it comes out only in the form of a wave, a light. So the radiation here, it's going to come out in the form of a wave or light. So let's, before we go in depth into the Bose model and the other models, let's in depth study about what is spectrum and how the radiations are being emitted in which form. So we all know that the radiations are emitted in the form of light. So how does this light travel? So in let's study about light. So we say that light is emitted out. Light is a form of energy. All of us know that light is a form of energy. Light is a form of energy. So how is this light emitted out? How does the light travel? If we take, light travels in the form of a wave. How does the light travel? It travels in the form of a wave. Imagine we have a pond, a big pond is there. So we have a pond with still water inside this. Let us imagine this is the pond with still water inside this. With still water inside this. So now what I am going to do is I'll put some stone inside. Still, I'm going to drop a small stone inside this water which is still. So when I throw a stone inside the water, what will happen? What will happen when I throw a stone inside a still water? You will see the production of ripples around, right? So let's me draw the ripple formation here with the blue one. So you will see a continuous, the ripples will be spreading out. So I throw a stone in the middle, and what is happening? You are getting ripples which are traveling forward. So till where will these ripples travel? Sorry. So till which point these ripples are going to travel? They will travel till the edge of the pond. They will travel till the edge of the pond, or if any obstacle comes in the middle, it gets bounced back, right? So let me draw the last one. It came out. Okay, let's imagine this is the last one. So here it has touched the edge of the pond. So what is happening to this? It will ripple back. So how is it going to bounce back? Let's use some other color to show this. I'll use some yellow color. So now what is happening to this wave? It bounces back, so it returns back. So like this, it's going to, you'll be seeing the wave which is bouncing back. So can we compare the light waves to the water waves? Yes, we can compare the light waves to the water waves. So just how the ripples are being produced and how the wave is traveling here, the same way the light wave also travels. So here if we take a light wave, what happens is just like the ripple, how I have shown the ripple. So these ripples are the elevated parts. Elevated parts means ridges. And the green part in the middle, that is the depression part, which is in lower part. So how can we show this? Is it goes like this. This is the lower part. The blue one is the upper part. Then the lower part and the upper part. So how is the water wave traveling? It is traveling with the ridges and depressions, and we call such a wave which is traveling in the form of ridges and depression, we call this as transverse wave. So what is the name of this wave? We call it as transverse wave. A quick recap of the different types of waves let us have now. This is called as transverse waves. So what are the characteristic features of transverse waves? We have two types of waves, transverse waves and longitudinal waves. In a transverse waves, longitudinal waves also, it's a small introduction I'll give about the longitudinal waves also here. So you know that transverse waves, if we imagine this is air and we have lot of particles. So let me put the particles in the blue color so that it is easy for us to understand. So let us imagine this is air and we have lot of particles. Air molecules are there which are very close to each other. Little distance I have put, okay. So let us imagine these are the air particles which are present in the air. So you are able to see, I think so. Let us imagine these are the air particles which are present in the air. So now what is going to happen? Let's create some disturbance. So what will happen when we create a disturbance? Each particle will try to vibrate. So any particle when it vibrates, how is it going to vibrate? So let us take this particle, let us imagine it will vibrate up to certain distance, up to this. I think the arrow has become very big one. I'll draw straight lines now instead of this. Okay. So let's see, imagine this particle, the second particle, let us imagine it has gone to little more distance. The third particle, let us imagine it has taken the highest position, maximum displacement it has undergone. This is the fourth particle which has come down. This is the fifth particle, right? So now let us see the other particles also. Let us imagine instead of going up, this is vibrating in the downward direction like this. This is going like this. Let us imagine one more particle is here. Let's imagine it has gone up to this point. The fourth particle till here, third particle till here. So now what is happening is all these vibrations are being passed from one particle to another particle. So how is this traveling means? It's traveling in the form of a wave. Let us join all the tips of these particles. So you are going to get a wave. You are going to get a wave. So you have an elevated part. Let's draw a straight line around the particle around which these particles are traveling. Let us imagine this one. So now you have, this is the elevated part, ridge part. This particle is undergoing maximum displacement, and this elevated parts, we call them as crest. I will use this text here. It's easy to write. So this elevated parts, we are calling them as crest. This part, the depression parts, which are at the lower part of ridge, they are called as troughs. So one crest and one trough will form a wave. So let us suppose you have another one here, the second one, it goes like this. So it's going to travel like this forward. So this becomes again another crest. This is the second peak. So these are two peaks. We have two peaks here. The distance between these two peaks, the distance between these two peaks is called as wavelength. So the distance between these two peaks, we are calling it as wavelength. The distance between these two peaks, we are calling it as wavelength. So this is called as wavelength. So what is wavelength? The distance between two peaks, we are calling it as wavelength. How do you show the wavelength? Let me write this here. Wavelength. Wavelength. So what is wavelength? It is the distance between two peaks. Two peaks. How do you denote wavelength? We have a Greek symbol to denote wavelength. It is called as lambda. So how will you denote wavelength? This is the symbol for wavelength. An inverted Y-shaped structure, we call it as lambda. How do we measure wavelength? It is done in centimeters, Armstrong units, etc. So whatever we use the units for measuring the wavelength there. The distance between two crests or two troughs is called as wavelength. Our distance between one crest and one trough will form wavelength. So that is the distance which the wave travels. Then we have one more term called as frequency. So what is frequency? Frequency means number of vibrations or number of wave peaks. So here it is not vibration. So let us take it in vibrations. We are counting it in terms of peaks. So let us take the number of peaks per second, that is per time. So number of peaks per second, let us take it as number of peaks per second crossing some place is called as frequency. So you have 5 number of peaks means it is 5 peaks per second. 2 peaks means 2 peaks per second. So as if the wavelength is more, number of peaks covered may be less. So the relationship between wavelength and frequency is inversely proportional there. So how are frequency and wavelength related? Inversely. That is, if we take wavelength is more, if we say wavelength is increasing, so automatically what does it mean? Frequency is decreasing. Frequency is decreasing. So this is what we concerned with transverse waves. So in transverse wave, you see the particles are vibrating perpendicular to the direction of propagation of wave. What is the direction of propagation of wave? I'll show it through the red line here. This is the direction of propagation of wave. So this one, back to this one, this is the direction of propagation of wave. So how are the particles vibrating? The particles are vibrating up and down like this. That is perpendicular to the direction of propagation of wave. So if the particles vibrate perpendicular to the direction of propagation of wave, we call it as a transverse wave. And if the particles vibrate parallel to the direction of propagation of waves. So in longitudinal waves, the particles are vibrating parallelly. Parallelly means to and fro. So let us imagine we have some particles. Let me show the particles here. This is one particle, this is second particle, third particle, third particle, fourth particle, fifth particle. Let us imagine these are the fifth. So let me draw 5. Now this will move to and fro like this. So how is the particle going to move here? It's going to move to and fro like this. So this is the direction of propagation of wave. The wave is traveling like this. So how are the particles vibrating means they will be vibrating to and fro. So because of this particle, if it hits this particle, which is the neighboring particle, that gets vibrated. Next it will go and hit the third particle, it gets vibrated. Next it hits the fourth particle, it goes and vibrates. So vibrations are passed from one particle to another particle. Once the first particle hits the second particle, again it will come back to its original position. So we will be getting places where the molecules are very close to each other, and you will be getting places where the particles are very far away from each other. So there the vibrations have not been passed. So you will be getting a wave like this where particles are very close to each other, and again the particles where they are little far away from each other. The place where the particles are compressed, we call them as compressions. So this yellow one, we call them as compressions, and the green one, we call them as, and the green ones, we call them as rarefactions. They're called as rarefactions. So you got the difference between transverse waves and longitudinal waves. Transverse waves, the particles vibrate perpendicular. Longitudinal waves, the particles vibrate parallel to each other. In transverse waves, we get crests and troughs. In longitudinal waves, we get compressions and rarefactions. Example for transverse waves is light waves. Example for longitudinal waves is sound waves. So let's go in depth into the transverse waves and how this light is traveling. So let's see what spectrum is, and how we have different types of transverse waves, how the light is traveling forward. So let me clear this board now. Let us imagine all of you might have seen, you might have played with your scales and everything. So I'm just going to put one small thing which all of you know. Uh, let me take a small prism. So you might have played with scale also. You need not use only prism, but you can also see a scale. Let us imagine this is a triangular prism which we have taken, and let us allow white light to pass through it. So let's see the white color here. This is the white light. Let us imagine through a torchlight or anything, through our sun, I'm going to pass white light. We are not able to see the light here. So I'll just put some black color here. Imagine this is the white light here. So let's put this. This is the white light. Let us imagine this white light is touching one face of the prism. So you know that the light has to travel straight like this, right? But what happens here is the light, instead of traveling straight, it bends. So why is it bending means this outside medium is air. Air is a rarer medium. While inside the prism, it is a denser medium, because glass molecules are there inside. It is a denser medium. Again, when it comes out, that would be a rarer medium. So what happens to the light now when it is traveling into the prism? Instead of traveling straight, what will happen is it bends. It bends. Now, again, when it is coming out of the prism also, it will bend and come out. So, but when it is coming out, you will see different colors of lights which is going to come out. So, you will see that something, 1 minute. So, let us imagine this has bent here. Now we'll take the other color. So you'll see the light gets dispersed. We call it as dispersion. When it is coming out, you will see the violet color will bend towards the base of the prism, and you will get different colors: violet, indigo. You will get blue color. We'll get blue color. Then we get green color. We'll get green color. Green, then we get yellow color, yellow. These are all overlapping without any gap here. Yellow, we get orange color, orange, then you get the red color. So red is going to undergo least deviation here. So you can see the formation of 7 colors in the, we don't have this indigo color. So let me put some pinkish color, but indigo is different color in the middle here. So you are going to get different colors. The white light is dispersed out into 7 colors. They are Vibgaya, that is violet, indigo, blue, green, yellow, orange, and red. And we call this phenomenon as dispersion. This is called as dispersion. So the white light has dispersed out into its 7 respective colors. The violet light undergoes the maximum dispersion here, the deviation, and the red light undergoes the less refraction here, less bending takes place for red light. So here, if we observe the in this range, that is violet and red range, if we take these 2 points here, what is happening here? Let us just take it out. So violet is having low wave. Okay. So here, violet has undergone maximum deviation. The reason is it is having low wavelength. So it has a low wavelength, and hence it is undergoing maximum deviation. The particles are very close to each other, very close. Here, so here, can we draw the wave here for to show the wavelength of the violet light? It is very close. So like this it goes, very close. So wavelength is very, very less. But for red, wavelength is more. So we can draw it like this. So here you can see the distance between the 2 peaks is more. The distance is more. So wavelength for red light is, red color is more. It is having high wavelength. High wavelength. So the wavelength is low means what does it mean? It is having high frequency. High frequency means energy is also very high. Sorry, energy is also high. Energy is high. Here for the red one, you have high wavelength, so it is having low frequency and its energy range is very less. So let's put the energy range also. Energy is less. Low frequency, energy is less. So this we are able to see when you have sent the white light, you saw the 7 colors, we are able to see. Since this 7 colors we are able to see, we call this as visible spectrum. We call it as visible spectrum because we are seeing it. And do you think above this visible spectrum and below the visible spectrum, do you have any other rays here, waves? Do we have any waves below and above this visible spectrum? Do we have any waves below and above the visible spectrum? We are not able to see it, right? So do we have waves above and below the visible spectrum? The answer is yes. We have, the answer is yes. We have waves which are below violet and which are above red. So what are these waves and why are we not able to see them? So these are the invisible radiations which are produced, and these also travel in the form of transverse waves. So this visible spectrum along with the waves which are above and below violet and red, we call them as electromagnetic, waves. And the range of wavelengths, the group of all these electromagnetic waves with different intensities, we call them it as electromagnetic spectrum. So what is spectrum? Spectrum is nothing but group of wavelengths is called as spectrum. We have natural spectrum. Can anybody tell me an example for natural spectrum? We have natural spectrum. We see it is seen in our atmosphere also, in our daily life also. When it rains and when there is a sun, when sun is there, and when it rains, what happens? When it rains, you will be having droplets of water in the air. You will have droplets of water in the air. That is, water droplets are present here in air. And when the white light, that is sun's rays, passes through it. So what will happen when the sun's rays pass through it? When the sun's rays pass through the water droplet, you can see the light disperses out into different colors. All 7 colors you can see. So the 7 colors you can see formation. That is because of, what do you call that 7 colors which you see on the atmosphere? In the atmosphere, it comes like a bow, isn't it? We call it as rainbow. So you have different colors in it. You have red in that. You'll see like this, right? Red color. Then you can see orange color inside that. We'll see orange overlapping of colors will take place there. Then you will see yellow color. Yellow color. Colorations have not come well because I have used broad sketch. Then you'll be seeing green, blue. So you can see a rainbow very clearly when it rains, and at the same time you're getting a sunlight there. So example of spectrum, a natural spectrum, is our rainbow. So how rainbow occurs? That's also because of dispersion. So let's see the entire electromagnetic waves and electromagnetic spectrum. Let me clear this. So now let us see what is an electromagnetic wave. First, let us see the characteristics of electromagnetic wave, and then we will go to what is meant by electromagnetic spectrum. So if we imagine we have taken a small charged particle, let us imagine. Let me put the charged particle in red color here. So if we imagine this is the charged particle, either it is a positive charged particle or negative charged particle, we know that this particle is going to produce radiations in all directions. So this particle, when it will produce radiation, when it is vibrating. So the important thing is a vibrating charged particle. So if you have a vibrating charged particle, what is happening to the charged particle here? The charged particle, when it starts vibrating, it will try to produce radiation in all possible directions. So this side, in all directions, it's going to produce radiations in all directions. This side also it will produce radiation. So when are the radiations produced? Means only when the particle is vibrating. The important thing is it should be vibrating. It will produce radiation in all directions. So you know that when a particle is vibrating in a particular place, automatically it is going to produce the electric field. So radiations are produced because of the production of electric field. So let us imagine we have a particle here. Let us draw the particle here. Let us imagine these are the particles we have here, which are going to vibrate. So when they vibrate, they start traveling, they produce a wave which travels forward. So let us imagine that the wave is going to travel forward in one direction. So let's take the direction of the wave is in this direction. Let us imagine the wave is going to travel in this direction. Then as the particle is vibrating, it is going to produce electric field. So in which direction is it going to produce the electric field? Means it produces the electric field perpendicular to the direction of propagation of wave. So, right, like put it like this. So this would be the direction of electric field. So let's put it as E vector. A bar has to be drawn on this, showing that it has direction. It's the electric field. So when we say that a charged particle is vibrating, it is traveling forward, it has produced an electric field. We know that according to electromagnetic theory, when a charged particle is carrying electric field, automatically you will develop magnetic field also. So if in your physics, you might have studied that if a charged particle is carrying electric field in one direction, how is the magnetic field developed around it? How is the magnetic field developed around it? In the form of loops you will be getting around it, right? Into the cycle. So the magnetic field is developed around the electric field in loops inside like this. So that is also going to be perpendicular. So let us draw the magnetic field. So when electric field is there, automatically what are you getting here? You're also going to get a magnetic field. This is also having direction. So let's put it like this. It has a magnetic field here. Let's show it as B. How do you show magnetic field? We show it by the symbol B. It is having direction. It's a vector quantity. It is also having direction. So put a bar on that. It is having direction on that. So this is an electric field. This is magnetic field. And this is the direction of propagation of wave. The direction of propagation of wave means what is it going to give us? It's going to give the velocity. So let us show the velocity with the symbol C. Velocity of the wave. So let's draw the electromagnetic wave and how it's going to travel here. So let's see how the wave travels. It's a transverse wave, we have said already. So the particles are going to vibrate perpendicular to the direction of propagation of wave. So let's draw first wave here. With red color it has come. I'll just clear this one's eraser. We'll go with another color so that it appears very clear for us. We'll use blue color. So blue color, we are using this to show the wave. So we are going to show the electric field now. Let us draw the electric field wave. So it travels in the form of a transverse wave. It goes like this. And how are the particles vibrating inside this electric field? If we take, all of them are going to vibrate perpendicular. So all will be straight lines like this, all straight, traveling in one direction, upward. You can keep direction also. You can also show the arrow for these particles as they are vibrating. So here you have the particles which are vibrating perpendicular to the direction of, sorry, let me just erase this, has gone wrong. So straight particles, straight waves, like this. This is an important question for diagram purpose. So you have straight, the particles are vibrating perpendicular like this to the direction of propagation of wave. Now you have the wave which is being produced because of magnetic field. Let us show this with another color, magnetic field. Let us use green color. This is also a magnetic field. So magnetic field, it's in bent way. The wave overlaps and it is slightly bent. It's like a loop, isn't it? So slightly bent over the electric field. So you will get a wave like this, which is overlapped. And how are these particles going to vibrate? They are also vibrating perpendicular to the direction of propagation of wave. So as the wave is slightly slanted, we are going to put the particles also like that only. So like this, slightly bent waves. Draw this diagram in your classwork so that you will get an analyzation of this. Make a practice of it. So these are the electromagnetic waves. So you can see it, only in one direction I have drawn it. If we can imagine it, this is oscillating. I am showing it as if it is stationed and how the particles are moving, right? So imagine this is all in oscillation. All the particles are moving. So will you see the wave like this? No, it's in continuous motion. The waves are continuously in motion. So it goes like this, electromagnetic wave, and the velocity of the wave C is given by a formula here. C is equal to frequency, it is shown by the symbol nu, and lambda. So how did we come to this formula, nu lambda? We know that velocity C is equal to, we have a formula for this. C is equal to, let me just erase this. We have a formula. C, velocity is equal to, velocity is equal to displacement by time, right? So here, velocity is equal to displacement means here, it is nothing but wavelength, that is the distance traveled, displacement by time, by time. So by time means here we have frequency nu is equal to 1 by 1 by t. Nu is equal to 1 by t. So you can write this formula as lambda into 1 by t is nothing but velocity, nu frequency. 1 by t is nothing but frequency. So velocity becomes C is equal to lambda into mu. Velocity is measured in meter per second or centimeter per second. So what are the characteristic features? Let's see the characteristic features of electromagnetic waves. Can we mention the points here? Electromagnetic waves, first point, the characteristic feature of them is they are transverse waves. Second thing, they are produced in oscillating electric and magnetic fields. That's very important. They're produced in oscillating electric and magnetic fields. Then they travel with a velocity equal to velocity of light. So what is velocity of light? It is 3 into 10 to the power of 10 power 8 meters per second. Velocity of light. They travel in vacuum They don't need a material medium to travel. They even travel in vacuum. So these are the important characteristics of electromagnetic waves. Let's repeat once again. What are the characteristic features of electromagnetic waves? They are produced, they are transverse waves. They are produced in oscillating electric and magnetic fields. And here one more point also, they are always perpendicular to the direction of propagation of wave, direction of propagation of waves. So they travel always, they move, their oscillation is perpendicular to the direction of propagation of wave. They travel with a velocity equal to the velocity of light, that is 3 into 10 to the power of 8 meters per second. They also travel in vacuum, and they also have constant amplitude. Their amplitude is constant. They have amplitude, constant amplitude, wavelength. As they travel, they have a constant wavelength also. So constant amplitude is there, wavelength is there, the frequency is also constant. So wavelength is constant means what does that mean? Frequency is also constant. So these are the characteristic features of electromagnetic waves. Hope you people have understood the electromagnetic waves and their characteristic features. So now let's go in detail with the electromagnetic spectrum. Electromagnetic spectrum. So about this electromagnetic spectrum, we said earlier that you have visible spectrum in the middle. Visible spectrum means which is seen by us, that all colors, that is what are the colors which we see? Violet to red. So you have here violet is there. So in visible spectrum you have Vidgayar, violet, indigo, blue, green, yellow, orange and red. So violet is having the least wavelength. Its wavelength range is around 400 nanometers. Red is having highest wavelength. Its wavelength range is around 700 nanometers. So beyond this region, you have infrared radiations, IR, infrared radiations. Then we have, after IR, you have microwaves, then we have radio waves. Space is not sufficient there. I'll just pull it out. We have radio waves. Then this side with the lower wavelength, you have below violet, we are having ultraviolet rays, UV rays we call them as. Then we have X-rays. Then we have gamma rays. Gamma is shown by the symbol here, Greek symbol, gamma rays. We show it like this and it's pronounced as gamma rays. So how will we pronounce this? These are called as gamma rays. So how are these waves? Let's just draw with so that you can have a clear understanding about their wavelengths. Gamma rays have the least wavelength. The wavelength of the gamma rays is very, very less. Very close, right? Very close. So as we go, we get X-rays. Slowly the wavelength will increase. Slowly the wavelength increases. As we go to ultraviolet rays, the wavelength still increases. As we go to visible spectrum again, the wavelength will increase. We have to increase it. Then infrared rays, still more the wavelength will increase. Microwaves, the wavelength still increases. Radio waves, the wavelength still increases. So as we go from left to right, so what is happening to the wavelength? What is happening to the wavelength? It is going to increase. So wavelength is increasing. So wavelength is increasing means what is happening to their frequency here? automatically what will happen to the frequency or energy levels? That would be decreasing. So which are the powerful waves having highest energy? Right. Gamma rays have high energy. Gamma rays have high energy. That's why we use them in treating cancer. So where are we using gamma rays? For treating cancer, killing the cancer cells. Gamma radiations, when they are focused into the tumor, it kills the cells. So cell division will decrease and growth of cells is restricted there. So that's why gamma rays are highly energetic. UV rays, you know, all of you, isn't it? In the hot sun, if we go, your skin gets red rash and all if you are exposed more to UV rays. So they are having high energy. Here, infrared radiations we use in physiotherapy for treating pains and all. Microwaves we use for cooking. All of you might have be knowing that you use micro ovens in your houses, where we use microwaves for cooking. In satellite communication also we use microwaves. Radio waves, you know, transmission, internet connections, radios and all, they are being transmitted because of radio waves. So slight disturbance is there in the atmosphere during a rainy season. We cannot hear the voices or we cannot see the picture clearly. Nowadays we were having Zoom classes, you could see the streaming was very, very weak, right? So as we move from left to right, the energy levels also decreases. So highest energy you have gamma rays. All these 7 electromagnetic waves, we call them as an electromagnetic spectrum. Group of wavelengths, we call them as electromagnetic spectrum. If you see an iron rod, if we heat it in the beginning, slowly the temperature will be increasing. So immediately you don't get iron, it needs lot of temperature to change into liquid form, right? Molten form. So here when we start heating the iron rod, first what color you will be seeing? Right, red. We'll see first red color. So as the temperature keeps on increasing, you will see the colors will change. It changes to orange, yellow, then you have blue, and even you can see white color when it is very, very hot. You can see molten iron in white color when it is very, very hot. So every element, so why are we studying about all this spectrum when we are concerned only about the atomic structure? So the main point here behind this is that every atom will produce a different intensity of light. So as the atom produces different intensity of light, it has a color. So the color also will change. For example, if we take copper, if you heat any copper in flame, you'll see green color formation there. That is the green means it is copper. So we can easily say, we can recognize an element by the coloration when it is heated. Because every atom is having a specific intensity of light. So when it emits a specific intensity of color light. Just like how our fingerprints, how can we recognize human beings? We say that in the world we have 7 types of people who will be same, but they will be same. But what is not same? Their twins also, everything will be same, but something is different in twins also. What is that difference there? Fingerprints. No 2 persons' fingerprints will match. The same way here also, how we recognize a person through their fingerprints, the same way we can recognize the elements by the intensity of light or coloration produced by the atoms. That's why it's very important that when we go deep into the study of level of atoms, atoms are invisible. So we are going to study about the spectroscopy, the spectrums which are being produced by these atoms, and recognize what type of element is it, what element is it, based upon their color production. So it's very important to learn about this spectrum before we go in detail with the structure given by Bohr, because Bohr could give his model based upon the spectrum which was produced by hydrogen atom. So about that we would be studying tomorrow in the tomorrow's class. Thank you.